Okay, we're going to combine these two sections here. Please, when you're using your textbook, there's a lot of additional information. You're welcome to read it. Okay, you're welcome to investigate and take a look at the additional stuff that I'm not covering here. But just so you know, okay, try and parallel your textbook reading with your notes. So have your notes with you so you know what you should be reading. Now, we're going to do several things today. First, we're going to look at the difference between a converging and a diverging lens. We're going to look at the applications of that. We're going to talk about the critical angle of a ray and identify what's called total internal reflection and its applications. And then third, we're going to talk about what's called atmospheric refraction and dispersion. Okay, those three things. Fernando.
Problem 07.
Yeah.
Cuando es due date?
The due date is at the top of your problem set. It says the 27th. Okay? It's on there online. Okay? Keep that in mind. That is a week from today. A week from today. I've already put up 15.2 and 15.3 problems last night, so you can see the updated version. We'll probably get through like 16.1, maybe 16.2 before the test. So there'll be one or two more additional sections I'll add by the end of this week. Yeah, but they're like 3 abridged chapters. We're not obviously covering everything in each section, okay? All right, let's take a look at this first diagram. Just draw it as easy as you can. So this is air at the top. This is glass. And then this is air. Okay, just draw a quick sketch of that. Yeah, Jeff.
Would it be a problem if we got a new notebook if we ran out of pages?
No, that's fine. Yeah, just keep that, please, because you're going to need it for your final. Yeah, that's what I was saying in the beginning here. I said you probably need 2 1-inch binders for the year. One for the first semester, one for the second. That might be it also.
I'm sorry I didn't know you had to
For this example, what we're going to think about here is the following. Imagine, and we talked about this last class in section 15.1. Light rays come in through the window, right? And immediately, when they go through a new medium, they get bent, okay? Or they get refracted or bent. What happens, though, is this. It gets refracted when it's inside of the glass, but then the light ray exiting the glass gets refracted into the air. So what you end up happening is the following. You get the air, which is a fast-moving medium, and there's the normal I've drawn. It bends toward the normal. So imagine this were the path of the light ray. It wants to follow this path right here, this dashed line. But what happens instead is it bends toward the normal because the glass slows down the wave. Then, after that though, it wants to continue and follow the path that it's currently on. So it wants to then follow this path right here. But what happens is, it then goes into the air from the glass. So now it speeds up the light wave. So instead of it bending toward the normal, let's draw another normal here. Instead of it bending toward the normal, what we see is that this light wave doesn't bend toward the normal, it bends away. So you get this like counterproductive situation, where it bends toward the normal and then away from the normal. Okay, toward and then away. Garrett.
What was the words that we used for smooth glass and then like
specular was smooth.
All right. What if it's not?
We're assuming specular surfaces. Yeah. When things change, when they're not specular, Garrett, a lot of differences occur. You have a lot more reflection. The reflection. Yeah. This does again. Refraction occurs with transparent specular surfaces. Yeah.
The normal is always perpendicular, right?
To the surface, correct. The dotted line is the path it would take had it not been refracted through the glass.
Alright, what if there was glass and there was another layer under that?
Of glass?
No, something else.
Then it would change again based on the n value, based on the index of refraction, using Snell's law. It could be like, it could be a bunch of different surfaces. It could go through a layer of water, then oil, then glycerin on top, then through glass, then into air. Imagine all those. It would be real weird. It would be different depending on the n values. It changes. Okay? Changes. Molly.
So when it goes into glass, it goes towards the normal.
When it goes into a slower medium, generally it goes toward the normal. So in this example, air is always the fastest medium. Anything from air is going to bend toward the normal. Anything going into air is going to bend away from the normal because air is always the fastest medium.
But it's supposed to be like exactly parallel to what it should
That's the key, and that's what you guys both noticed that? Good. And that's what we're looking at today. The fact that our original light ray is pretty much parallel. The original ray, take a look at it.
If it's not specular, it's not going to be parallel in the end.
Yes, correct. If it's not specular, you're not going to get this example here. So what you notice is that the original light ray, if followed, is right here, right? It's parallel to this one. They're parallel to one another. So you might ask yourself, if I want to change the direction of the light so that I can maybe wear like glasses, for example, if I just put a normal piece of glass in there, is it going to do anything? No, it's not going to do anything. Because if you put a normal piece of glass in eyeglasses, it won't do anything. Because it's not changing the focus of the light rays. It's not going to cause it to change in your eyes. So what you get is these fake glasses, pretty much. It's like the glass in the window. If you look outside, you're not going to see any distorted version. If Masha were to open that window over there and we kept looking outside, it would look the same. It wouldn't change. Nothing's going to change because the glass has no real effect. But what do you guys know about glasses and contact lenses? Are they flat surfaces? What are they? They're rounded or curved. And the curvature is what causes the change in the light rays. Max?
Wait, there's no distortion at all, like not even like microscopically?
I mean, microscopically, absolutely, Max. Absolutely. But not to the effect. It is negligible. Okay, that's our favorite word in physics is negligible. Because it really doesn't matter. Okay? Like we talk about how air resistance is negligible in the projectile motion problems. Okay, for the sake of this, yeah. Okay? Now, again, the idea is that glass that is not curved or a pane that is not curved does not affect the overall direction of the light. What does it do though? It causes this shift. There's a shift here. Okay, there's some sort of a shift. You can call that like a delta. Okay? The light rays have been shifted. And you've seen this before. When you study parabolas, here's the equation y equals x squared. Oops. Okay, y equals x squared. I'll be exaggerative for the next one. The equation of this now, let me draw this new graph.
These are rays, right?
Okay, the equation of y equals quantity x minus 3 squared, we all know looks like this. Okay, it's shifted over 3 units to the right because of the horizontal shift. That's what's happening here. There's a shift in the light rays, but it does not affect anything because don't we know all the light rays, don't they not, there's not one light ray coming in. What happens? There's a whole bunch of them coming in, right? And here's what they all look like. These are all the incident light rays coming in. So even though we see a shift, the shift does not really affect us at all because they're going to shift on top of one another. It's not going to affect it.
That's the x minus 2.
Say again?
That's the x minus 2.
Louder, Jeff.
That's the x minus 2.
The x minus 3 is the example, this red curve right here. Is the idea of a horizontal translation or shift that you learn in Algebra 2. Yeah, but it's not like, this is an angular shift. So it's part horizontal, part vertical, and that's why you see this delta right here in this direction. Okay? The important part is not which way it's shifted, the idea though that it is shifted, but not angled at all. The angle is not changed because it's flat.
Is this example like a window?
Yes, that's exactly what it's like. This is like a window. Let's now take a look at an example where we have maybe something like an eyeglass. Okay?
Typical adolescent version of the ant with the magnifying glass.
We'll get to it in last class also. Okay?
I always wondered how to do this. I always wondered.
All right, let's take a look at this now. To focus, we'll talk about it. To focus or change the direction of the light, the surface needs to be curved, like we talked about, and we call this a lens. A lens is simply a transparent object. A lens is simply a transparent object that refracts light rays and causes them to either converge or diverge. Okay, it causes them to converge or diverge. Converge or diverge. Say it either way you'd like. Now, let's talk about what this actually means. Those of you in pre-calculus might have heard of converging or diverging functions. Okay? You might have heard of that before. You might have heard of something like a converging sequence or series, or a sum of a sequence or a series. But that doesn't really matter right now. Okay? It is analogous, but let me give you an example now of what we're talking about. Converging simply means that the light rays are now focused on a point. For example, Fernando, when you're a kid, what do you do with a magnifying glass? Or what? Burn stuff. Some kids take magnifying glasses and they focus the sun's light rays on a leaf on the ground, which might cause the leaf to burn, right? Not on a bug, which is cruel and mean.
No, or like when you're sitting in the back of the class and you take like a shiny like plastic book cover and then like put it on the
Or your watch lens, exactly. Okay? If you take your watch lens and you aim it, sometimes it might focus. Okay? Now, Paul, to know though, the lens of your watch, or the glass on your watch, is not a lens, it's a flat glass. So this will not focus the rays, it'll just redirect them. You're reflecting there, Paul. You're reflecting. You're not converging, okay? No, it's neither. It's just reflecting. Diverging, Jeff, is when you have light rays that are coming in parallel and they pass through this concave lens, causing them to separate from one another. Okay? Have you ever looked in a flashlight? Ever look at the lens inside of a flashlight? Okay, you can focus it. The light rays diverge, don't they? Isn't this a flashlight here on the right? On the right it's concave, on the left it's convex. Remember, concave is when you have like a cave in the wall. There's a cave. Okay, convex is when it bows out in the middle. So, we call this a focal point. And it looks at first as if a diverging lens does not have a focal point. That's FP right there. Sorry, you can't see it because of the color. That is FP right here. Come on, guys. It looks as if a diverging lens doesn't have a focal point, which I would say right away does make sense. But if you take the path of the diverging rays and trace them to the beginning, there actually is a focal point. It's just virtual. If you were to follow these paths back, there is a focal point here. Okay, but don't worry about that focal point there, because it's called a virtual focal point, and we're not going to get into that. Okay? They don't. So that's why it's called virtual. It's not real, Jeff. It's virtual.
Wait, so why does the light, like, it's a watch, it just reflects and it's going to go like...
Because the watch is not bent. It's a glass pane that is a flat surface.
We just did about page 4, it goes straight through.
Well, yeah, some of the rays come through, but some of them reflect. Off any glossy surface, there's reflection. There's also refraction. There's both. Yeah. We were talking about specifically refraction. Some of the light does reflect off the surface, though. Jack?
Where's the focal point on the second image?
So on the second image, there is no real focal point. It's behind the original. It's like a virtual focal point. We don't really worry too much about it. Okay, so you don't even have to draw it if you don't want to. But just so you know, there is a focal point. Okay? All right, let's take a look now at application, or an application of this. You do not need to write everything here. Okay, you do not need to write everything, but let's talk. There are two types, generally speaking. There are more than this, but there are two types of corrective lenses. Ones that correct farsightedness, ones that correct nearsightedness. Okay, and some of you might have questions, but let me talk for a little while, then I'll take questions. So to generally give you an idea of what's going on, focus right now on these two diagrams. Don't focus on the right ones. Those are the corrected ones. Hyperopia, I think is how you pronounce it. Hyperopia?
Hyperbolia.
Well, this is myopia. I know that. I think this is hyperopia. I don't know the exact pronunciation. But what it is the following. Someone who is farsighted can see far. They cannot see up close. Okay? Someone who is nearsighted can see near and cannot see far. Let's take a look at the first scenario, farsighted. Here's what's happening. And I'm going to trace it with the tracer on here, because if I draw, it's going to end up a mess. Light rays come from some focal point toward your eyes. Okay? Then the light rays hit your cornea And then they get focused additionally through your lens in your eye. And then they want to focus on what's called the retina. The retina is this surface back here. If they are focused too far, farsighted, too far, what happens is the person can see far still, but they can't see up close. So they need corrective lenses so that they can read a book, for example. Now, if they come in, and the light rays come in, and they are focused too soon, too soon, then the person can see near, but they cannot see far. So what we need to do is correct these with lenses. And here's how it works. If the light rays are focused too far, you want them to come together sooner. So you want to focus them earlier. So you put what's called a converging lens there, ahead of it. See, here's the converging lens right here. So now what happens is, the rays start to converge earlier. So the rays converge at this point in time here, earlier, which causes them to hit the retina earlier, or to focus earlier, which lands on the retina instead of beyond the retina. Okay, so it corrects it with a converging lens. But in the other case, when it is focused too soon, you want the rays to focus a little bit later. So you might separate them a little bit first with a diverging lens here. It causes them to separate, and then they come back and they will focus directly on the retina. Okay, directly on the retina here. So when a person is nearsighted, what happens is the rays focus too near to the lens. So you want to separate them, which gives it more time to focus later on. Again, when it's farsighted, they focus too far down the road. So you want to put a converging lens here so that they focus earlier and they focus right on the retina. The whole idea is to focus on the retina.
So when old people lose their eyesight,
It's your eyes changing shape.
yeah.
Okay, your eyes change shape over a long time. Okay, I mean other things affect it as well. Like people that get glaucoma, there's a lot of other issues.
Or both.
When people get older, usually they lose their nearsightedness. Usually they cannot see up close, so they wear bifocals, okay, or reading glasses. If a person cannot see far when they're a kid, but they can see near, but then when they get older, they can no longer see near either, they wear bifocals. And what bifocals do, well, first of all, who invented bifocals?
Benjamin Franklin.
Ben Franklin.
Yeah,
That's
he's
right. National treasure right there.
Okay? Bifocals have a split pane. The upper lens is a converging lens because it helps you see far, which is the first case. The second case is a diverging lens. That's this part right here. That's diverging, and this is converging. And what happens is, if a person wants to see far, they need to use a converging lens so it focuses the retina earlier. But then when they want to see near, they use a diverging lens. You don't see many of these anymore. What do you see now? Anybody know the term now for the glasses that are used instead of a bifocal? It's a new term. And you probably don't know it because you don't have it. Your parents probably do. It's called a transition lens.
They just have the
Okay?
Darker as the sun.
But there's also transition as far as the actual prescription goes. Transition, you see, yeah, you do see the change in the color for the sun. But there's also ones that have a transition in the glass itself. You don't see the split pane anymore. Okay?
What will I think of next?
What will they? I don't know. I mean, there are a lot of things. Molly.
When a person gets laser surgery,
Uh-huh.
they cut off the first part of their eye.
They don't cut off. They put slits in the eye. And those slits change the angle of the rays coming in. That's all it is. Okay?
Well, because I was watching Kim Kardashian's
Uh-huh.
like last year, and Kim got.
Oh, last year, not like maybe yesterday.
No, it wasn't yesterday. And
Listen, guys, stop.
It was really gross. Like her eye was open, and they're like, "Kim, this is her son." They just like cut off.
We should watch that episode in class. I really hope
So they're taking the lasers and they're cutting little slits into your eyes, and those
Have you
focus
seen
the
that
light
episode
rays.
of Kim Kardashian's with Ray J?
Jack,
Yeah.
not on point. Come on. Now, if somebody gets laser surgery, it is very useful because it takes away the fact that they need to use maybe bifocals when they're older. So they get the laser surgery to help them see far, then they get, just one pair of glasses and they put them on maybe when they're only reading. Okay? Only when they're reading.
My dad got that, and he said in the morning he can't see, like he's completely blind.
It takes time for his eyes to adjust to the day. I could see that.
Really not like it.
I mean, you got it a while ago. It's better than they were.
All right, this next thing is extremely, extremely confusing. And the last class had a tough time wrapping their head around it. And the book does not do a great job of describing it. So what I recommend you do for now is draw the diagram. And there is a red ray here, just so you know. There's a ray here. Make sure you draw it. I'm highlighting it right now. This ray right here is on the surface. It's on the surface boundary between the air and the water. So you need to draw this one. It's not, just like a black line. It is a red line there.
Yeah, but water.
Emphasize it.
Water's not smooth.
When it's still, it is.
Still,
Like on a lake with
It's
no
same.
Can you see your reflection in the lake?
Yeah.
Maybe I can.
There's your answer.
Maybe he's a vampire who has no reflection.
Take a minute to draw.
Is there external reflection? That's a good question.
So the more of an angle you go at, the more of an angle.
No, that was a good question. You just didn't know that's the problem.
Very good, Gary. Very good. And that's what people are having trouble wrapping their heads around. Very good. Max.
Yeah.
Is there external reflection?
There is. External reflection is what you see. So when you look in a mirror, that's external reflection. Or when the light shines on these glass panes, and some of it comes through the glass into the room, and some of it gets sent back out into the city, that's external reflection. Internal reflection, internal, is when it comes from some medium of slow wavelength, like water, to a fast medium like air. Or like a diamond, and we'll talk about that, how a diamond traps waves. Okay?
Wait, what? It does what?
Traps the waves.
It does that.
Ever seen, what the best example is? This is really not true or not correct physically or mathematically. Who's a fan of Superman?
Oh, man.
Got some Superman fans? All right. So, you all know what they call when do you ever see the original movies or no?
Yes.
Okay. Or Smallville, one or the other at least? Okay. Now, you know how Superman traps, who's his arch enemy? Not Lex Luger, not the arch enemy from Krypton. General Zod. General Zod. He traps him in this like diamond in space, and he's like floating around in it. If you've seen the original, he traps him in this it's like a fortress in a sense. It's another dimension. He traps him in there, and it actually looks like a diamond, and he's trapped inside of it, and he can't move. It's a good analogy to the idea of how light rays are trapped inside. It's not physically true, obviously, okay? But the idea is there, and that's what we're going to look at now. Okay, so just listen to me for a little while first, and then I'll take questions.
Wait, did you ever get those tests back? You just give us the grades.
I just gave you the grades. I'm going to try and do it tomorrow. The other class, I ran out of time at the end. They're all here. It's all stacked. So, let's take a look at an example. Now, we've got the same example here. So there's water and there's air. And I'm going to go one at a time. So imagine a light ray hits the surface, perpendicular to the surface. We talked about in class how it's going to pass directly through. Okay, that's the first light wave in this example. Next. The next light wave, let's say we change the angle of the flashlight. And it comes like this. Guys, again, I'm taking questions after I talk. You need to listen and stop talking. Too much chatter. The next light wave is going to be bent. Okay, it's going to be bent away from the normal. Okay, away from the normal. After that, the next light wave that hits it is going to continue to be bent, but because the incident ray was more at an angle, this next one is going to be at more of an angle. And what you're noticing is that the refracted angle and the incident angle are functions of one another. And here's what I'm talking about. Here's the normal. Here's the normal at this point. Here's the incident angle. See how small it is? Well, the refracted angle is also relatively small. But then when the incident angle gets bigger, the refracted angle gets much bigger. So as the incident angle gets larger, the refracted angle gets larger. There's going to come a point in time where the incident angle is so great, here that the refracted angle gets to be 90 degrees. So let's give numbers for examples. These are not correct mathematically. These are completely hypothetical. Let's say this is 10, this is 30, and this is 45. This may be 30, this may be 60, and let's say the next ray is going to become simply 90 degrees. What happens is this. And this is, again guys, these angles are not meant to be doubles and stuff. These are completely hypothetical numbers. Don't read into them. But as the incident angle increases, the refracted angle is an increase. And we know that because of Snell's law.
Is that statement always true as incident angles?
From Snell's law, we know that as the incident angle theta I increases, the refracted angle theta R is going to increase. But there's going to come a point where theta R becomes 90 degrees. It becomes 90 degrees. Now, when that time comes, we call this the critical angle of incident ray. So notice this theta C in the diagram. Theta C. When theta R becomes 90 degrees, we call this the critical angle now. Okay, the critical angle. Now, what happens, and you look in the diagram now, so look back over here, please. What happens when the angle becomes greater than the critical angle is instead of it becoming parallel to the surface, it actually gets trapped inside the original medium. It gets trapped because of the fact that this angle now, this angle here, is bigger, this theta is greater than the critical angle. When the angle is bigger than the critical angle, it will automatically refract the light into the medium. Okay? And we call this internal reflection, or total internal reflection. This is how a diamond works exactly. The light ray passes into the diamond, it wants to escape the diamond, but it hits the diamond at an angle that is bigger than the critical angle. And the critical angle in a diamond is very low, which means that a lot of the rays will be greater than the critical angle. So a lot of the rays get trapped inside of the diamond. That's what causes it to sparkle. That's why it glistens, okay? And yes, you're already saying the song. So again, your theory here is as theta I increases, theta R increases, until theta R becomes 90 degrees. Okay, until theta R becomes 90 degrees, like in this example here, and the light ray is on the surface. We call this the critical angle. Anything bigger than the critical angle, 45.1 degree, will get internally reflected. 47, 48, 50, 70, all those angles, up till 90 obviously, okay, are going to cause total internal reflection. What happens at 90? It doesn't make sense. It'd be a light source here, and the ray would look like this. Okay?
That's not possible.
Okay? It would just run along the ray like that.
What about if it's like 100?
Well, then it would be coming from out here now, right? If it was 100, it would be coming from out here. So it would now just get reflected, and part of it would get refracted, and we don't have that example. Again, here's another stipulation you must write down. The light or the ray must travel from a slower moving medium to a faster moving medium. So it has to go from something like water to air. From a slower moving medium to a faster moving medium. Okay? Air to water, you will never, ever, 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 ever have tonal internal reflection. Okay? It will not happen.
Wait, air to water, you said.
Correct. This is from water to air.
Okay.
This example is your example like an aquarium or a fish tank. If you have a fish tank and you have a light source at the bottom, you'll notice in the aquarium, you walk around the aquarium, it's very dark. But inside of the fish tank where the fish are, it's very bright. You ever notice that? How do they do that? They have the light set up so that the angle that it hits the surface of the water is enough so that it gets internally reflected. So the light gets trapped inside of here, giving the fish some light. Okay? That's what's happening there, really. And the dimensions of the light of the tank itself, and the light source, and the angle of the light source all affect these problems.
This might be totally wrong, but you know when you're like looking at a mirror from like an angle, if you look at it like a small enough angle, you can only see like what's in like on your half, I guess. But if you look at it like straight on, you can see farther.
A lot of times with mirror.
You can see far? That's funny. You can see farther?
No.
That's just strict reflection. That's not internal reflection at all. So it's not applicable here, to be honest. But the idea is true of what you're saying. Of what you're saying, yeah. Paul.
So for the
Listen, guys. Paul.
theta subscript c, if that's like totally internal reflected, how does that new angle compare to the original? Is it the same?
So theta c is not like a new compared to an original. It's a breaking point. So if I took a flashlight and shined it like this, Paul, okay, so the rays are going to pass through. I shine it like this. The rays will pass through, but they'll get bent. But the minute I get to around the critical angle, the rays are no longer going to pass out of the water. They're going to get reflected into the water.
What would that angle be?
That's what I'm going to show you right now. That's exactly what I'm about to show you, okay? Hold on one sec. Max.
So, ever since I was a little kid, I wanted one of those fish tanks, you know, like go around the stairs and there's like sharks in them and stuff.
I go around the stairs.
Alright, they're just like around the walls and they're circular, like it goes around.
Interesting. Never seen that. Go ahead.
Oh, I was just wondering how like the light would refract. Like, there's like one light, like in the
It's like he's saying instead of a wall, it's like a fish tank.
Yeah, but it's like circular.
And it's
So I was just
curved.
wondering-
And there's one light source at the end, and somehow all the light goes through the whole thing.
Yeah.
It's probably the curvature of the glass itself. Yeah. I've never seen that, but that's my guess. Yeah. There's probably internal reflection going on there.
Okay.
Wait, I was just thinking about the example you made with like at an aquarium. If it's aimed at an angle where it doesn't go out of the tank, but it comes back in, like the one that you drew, wouldn't it hit the glass?
Yeah, and that's the thing. So you want to. They try to optimize it so that a lot of the waves keep bouncing off and keep staying within the glass itself. Some of them do pass through, obviously, so that we can see what's in there. If light waves didn't pass through the glass, we would not be able to see what's in there. So only some of them do, and that's why when you look in there, it looks a little bit fuzzy or distorted sometimes, because only part of the waves are coming through. Okay. To answer your question as to what theta I becomes, this is what we're going to talk about now. Okay.
Wait, what happens if the light ray does go from faster to
From a faster to a slower, there's never internal refraction. Ever. And we'll talk about it here. And I'll give you a reason why. So when the refracted ray is parallel to the surface boundary, we say that theta I has become the critical angle. Okay, that's what we talked about a minute ago. We can also say that it is perpendicular to the normal. Okay, thus theta R is 90 degrees. Okay, and if we look back at our diagram here, let's take a look. We have some light ray that comes in at the critical angle. Here's the normal. Here's the critical angle. The light ray is refracted along the surface, which means that the refracted angle is 90 degrees.
Does that say theta I is equal to theta C? Oh.
Correct. So when the refracted ray is parallel, we can say that it is perpendicular to the normal. Now, what does that do to our equation? Let's take a look. Well, theta I, the incident angle, is the critical angle here. You do not have to write word for word, okay? You do not have to write word for word. So again, when the light ray comes at an angle, okay, that's a critical angle, what happens is the refracted ray becomes parallel to the surface boundary, which we can say is perpendicular to the normal. So theta R becomes 90.
What exactly in words do we get? From snails.
If you want to write in words, write it down there. What we get is this equation. Okay, that's what I'm going through. Snell's law is not words, it's an equation.
Have you ever seen that? No, you didn't.
Yeah, you can. I can. In your textbook, there's an image of a flashlight underwater changing angles, and they show the paths, and you can see the light. And at one angle, you'll see that there's a light ray, and then no ray comes out and no ray comes back in, but you'll see a bit of a hint on the surface, and that's where you're seeing it. Okay? It actually does exist. So what happens is this. You have Ni, theta I is now critical, and theta R is now 90. Okay?
Why did theta I turn into theta critical?
Because remember, this is the incident angle, theta I, and it's always called theta I, but at some point it hits this number, some number based on the medium, that causes it to become critical. Okay, critical in nature, meaning anything beyond that will cause total internal reflection. Now, if we think about this, what is the sign of 90? Who knows the sign of 90? It's 1. Okay, it's 1. So it doesn't really affect the problem. Now, get rid of the Ni, because we want to determine the critical angle.
Why can you just do that?
Well, not get rid of, but divide by, I mean. Okay? Divide both sides by Ni to get sine of theta c by itself, because we're trying to find what the critical angle will be. And we can find the critical angle between any two mediums just by looking at this formula. Who remembers from last class? How do I get rid of the sine?
You do the opposite.
Yeah, we call that the... Good, Jeff. Very good. The sine inverse.
I thought that was the conjugate.
It's the inverse. Inverse. The conjugate is like 2 plus radical 3, 2 minus radical 3. Those are binomial conjugates in math.
That's just where you hit second. And then
Yes, correct. Absolutely, Jack. Good. Now, what you'll see here is that theta c is simply the sine inverse of nr over ni. In this case, go back, please, and look at the example we had up here. We went from, I'll redraw it down here. We went from water to air. Okay, and that's what happened here. We had some sort of internal reflection. So, the incident Ni is the eye of water. Wherever it comes from is Ni. Okay, wherever it's coming from, the source of which it comes from is always Ni. The medium that it's trying to pass into is always Nr. Okay? So again, slow speed wave to a faster speed wave. So Ni for water, for example, just so you know, is 1.33. And the N for air is 1.0. So if you wanted to know the critical angle from water to air at which you need to shine a light in an aquarium, just do the sine inverse of, in this case, 1 over 1.33.
I don't really know what's going on.
Okay?
And that's a constant.
And it's a constant for all water to air. Okay? Again, assuming that you're at a constant temperature and pressure and all that other fun stuff. But what's happening here is this. You want to determine the critical angle. That's the goal for all these problems, is determine theta c. To do so, you need to use this formula, which, by the way, I will give you this formula on the test. You don't have to derive all the work we just did. I wanted to show you where it comes from, though, and the reasons for it. But using this formula, if you have to determine the critical angle between water and air, you need to remember that it can only go from water to air. The critical angle cannot occur in the opposite. Okay? And if you try that, flip the 1.33 and the 1 around, you'll get an error on your calculator. Okay, we'll talk more about that next class. That's exact. I'm going to be available today from 2:20 to 2:50. Okay, 2:20 to 2:50. We left off yesterday talking about the critical angle. Okay, now what we're going to do is look at an example of a problem that involves a critical angle. Remember your formula for the critical angle. We solved this, or we derived this yesterday. Okay, it's going to be theta c equals sine inverse of nr over ni. Okay, nr over ni. Here's another thing you can remember. And this is just like a fun fact. And you'll learn it this year in Algebra 2. You cannot do the sine inverse if this is a number greater than 1 inside of here. So nr for these problems, the numerator will always be less than the denominator. So if you don't know which one is NR and which one is NI in this problem, so for example, determine the critical angle for light traveling from diamond into air. Well, diamond is the incident one because it's from diamond. So this is really, this here is going to be your NI because it's from diamond. Remember, whatever it comes from is the incident material. Whatever it goes to is the refracted. So the air, which we know N is 1 for air, that's going to go up top up here. And if you say you forgot that, try it on your calculator. If you try to do sine inverse of the other way around, if you do it as 2.419 over 1, you're going to get an error. Because the sine and cosine functions only exist as if their value must be between 0 and 1. Okay? It cannot be anything greater than 1. It will never be. It's a mathematical impossibility. So if you were to make believe you mix these up, you're going to get an error in your calculator. And if that comes into play, it means, oh wait, I screwed that up. I switched them. So that's an easy way to check that you're doing it right. Is that clear? So again, if you mix them up, you're going to get an error. So for this problem, since we're going from diamond to air, diamond is your incident material. Okay? Air is your refracted medium. So the air is going to be NR, and the diamond goes in for NI. Go ahead, Fernando.
We're going to be given a chart, right?
You'll be either given a table in the beginning of the test or the end of the test with all the values, or I will just simply put the value in the actual problem. You do not have to. You need to know air. Air is 1. Only one you need to know. Everything else you'll have to read from the table. Jeff.
Isn't diamond going from a slower, a faster?
Diamond is the slower one. Remember, air is always the fastest medium. Air is always the fastest medium. No, not as you can go from diamond to water, because water is faster than air. Okay, so as long as your NR value here, or your NI value for the diamond is bigger than the air. Okay, so it doesn't matter what medium, as long as you go from a slow moving medium to a faster moving medium, the incident or the critical angle can exist. Okay, Olivia.
If light was in a vacuum, would it go even faster than...
Say again?
If light was in a vacuum...
We're calling that air. Air is considered to be a vacuum. So we're assuming that it is, yeah. Okay?
What if it's not in a vacuum?
If it's air that's not in a vacuum, the actual number, the actual number would slow down a little bit. But we're assuming that it's 1, even though it's 1.0000 and then there's a few numbers afterward.
Facebook status, here we go.
Okay, so is the answer 24?
Let's figure out. So it's 1 over 2.419.
Jeff, we got any trouble.
Okay? Now, 2 things. First, make sure your calculator is in degree mode, or your answer is not going to be given in degrees. Second, you have to make sure you press second and then sine to bring up sine inverse. This is not sine regular, this is sine inverse. And Maya, what did you get?
24.4.
Sounds good to me. Is that rounded appropriately?
Yeah.
Fernando, can you check that, please?
That's what I got in my notes, so it looks good to me. Okay? Now, let's discuss what this means. This is the important part. The answer, what does that actually mean to you? Okay? The critical angle. Here's what it means. Any angle bigger than 24.4 degrees from a diamond to air will automatically reflect the light back into the diamond. It won't actually pass through. So for example, if you have an angle, so you're looking at like a diamond ring maybe or something, right? And there's light that comes in. The light goes to exit the diamond. If it hits the diamond surface going into the air at an angle bigger than this, which is a lot of angles. Think about that. Any angle, don't keep moving up. I know what you guys are doing.
It's a race. It's a race. We are in trouble for
So, everybody slowly moves up, and by the end of the class, I'm just like this.
No, you know Mr.
I'll tell you some good ones at the end of the year that you can do.
Mr.
Not
in freshman year, we had it for algebra.
No.
We had it for algebra 1. Me and Tyson literally were like right in front of her, like at her desk, and she said,
What we're going to notice here is this. Any angle bigger, listen gentlemen, any angle bigger is going to cause total internal reflection, which is why, again, we talk about how a diamond ends up sparkling the way it does. If you were to try this for something not a diamond, say for example water, where the N value is 1.3 repeating, well notice for those that we're not going to end up getting an angle like 24.4. It'll be an angle somewhere like, say, in the terms of like 45 or 50. And what that means is that not as much of the light inside of water ends up getting reflected back in. Okay? So again, anything bigger than theta C causes total internal reflection.
So
Anything larger than theta C, the critical angle, causes total internal reflection. I'm guaranteeing you that now. It'll be some sort of question on your test with that. Okay? Fernando, you got to hang up.
My question was reflection or refraction?
Refraction. Well, okay. Again, let me go into a little detail here. You have refraction until you get to theta C, then everything is reflected internally. Okay, then everything is reflected internally.
Total internal
reflection.
You don't have refraction.
Correct. When you have
total internal.
Yes, exactly.
Because
refraction ceases to exist.
You can simply think about it. It just doesn't travel through.
Yeah, it's like exactly. It's coming back, so there cannot be refraction. That's exactly right.
So if it's theta C or smaller, it just bounces right back. It's refraction.
No.
If it's theta C or smaller, there is refraction, so it passes through. If it's bigger than theta C, there is no refraction. It gets reflected back into the medium it came from. Okay, back into the medium it came from. Even if it's a translucent surface, which is the phenomenon, that's the idea. Think about it for a second. If you shine a light from water to air, it should exit the water. But at a certain angle, it's going to stop exiting the water, and it's going to actually come back in. And it's going to make the surface of the water act like a solid surface, like a mirror, which is kind of crazy to think about when it's not. Okay? All because of the angle.
What if you take distance like
No effect.
If you go to the bottom of the ocean?
Well, technically, then we have to talk about brightness, and we talked about that in section 14, where the brightness reduces over a certain distance. So the light might not make it to the surface there. That's different. But if you have like intensity that's different by a little bit, it won't affect it at all. Not one bit. Okay? All right. Last thing to do here. Talk about two topics. First, we're going to look at an application. So we're going to look at the application of total internal reflection. I got to go to the next slide. There we go. Okay.
The critical equation. Critical angle equation.
Theta C equals
Sine -1 NR.
Yep.
I thought that was the derived.
So, one application we're going to talk about, there are many applications of this. There are many. But one that is the most common one that you see, that most people don't realize that's what it is fiber optics.
Oh, right.
Okay? People talk about like Verizon Fios and fiber optics, what they are. Here's what they are. Okay? Imagine if you have something called a light pipe. Okay? A light pipe. And what a light pipe is, it's made of a material, traditionally some sort of a glass material or a flexible glass, and you can see it, you can't really see it too well here, but have you ever seen those here you can see it better on my iPad, it's not projecting well on the board, or let me shut this off, it looks better. Yeah, you can see a lot better now. So these are all these little strands, and they glow at the end. Okay, but the actual, what is it though? There's a name for it.
You get it like a museum or something.
I don't know what it's actually called.
Each strand has like
Yeah, each strand is its own light pipe. Okay? And at the end of the light pipe, you can see the light, but not from the walls, because none of the light is passing through. That's the key. The walls of all these cylinders, and you're seeing a close-up over here. So again, the close-up is right here, but the walls of all of these cylinders here are reflecting the light totally, internally. So you have total internal reflection from the walls, but when it gets to the end of the light pipe, there's no casing at the end, so the light shows only at the ends of all these tips here. And this is what's going on. The angles here are all staying, or the light ray is reflecting inside of the light pipe, and then it exits at the very end. That's what you see. So only the end reflects it. This is used widely in fiber optics. If you want to send a light signal, if you're using like Fios, Verizon Fios, this is actually what's happening. The signal is getting totally internally reflected inside of the light pipe underground. and it's projecting that signal at your home, which is why you get a much better picture with Verizon Fios than you do with other cable providers. It's the truth, you do. Because it's able to transmit more data by using this. Okay? So they're flexible light pipes.
I put one of those in the microwave.
How did it turn out? Not good. Yeah. I don't imagine it would.
You did Verizon
I was
Fios
like
commercial,
eight
they're
in my
bugging
minutes.
so many more customers.
I doubt it.
I'd buy it if I was
Okay, but this is the reason that it does actually work better.
Sucks, though.
Depends on where you live, really.
Yeah, Arizona, that's not good.
I have Time Warner Cable and it's terrible.
Yeah, that's why I had
Time Warner Cable is the worst.
It's awful.
I don't think it's that good.
Well, where I live, it's really bad. Depends. In the city, there are good parts, but I live in Brooklyn, and it's terrible. All right, so that's one application of total internal reflection. Last thing to discuss here. We're going to talk about something called dispersion, which you've seen many times, but I want to quickly give you the definition. All right, it's the process of separating, which is refraction, by the way, but separating white light into its component wavelengths. So if you've ever used a prism before, you've all seen this. You take light, you hold it up to a prism, and you see like a rainbow on the ground. What's happening is the light that's white is getting bent to different wavelengths, and you're seeing all the bends. And those bends there show the different colors. So the angle at which it's bent is what's determining whether the light is red or blue or indigo or green or orange or yellow or any of the colors of the spectrum. And take a look at the prism. The light comes in, it gets bent, and the angle that it gets bent at determines the different colors. Okay? Now, what you'll see is that this also causes water droplets to produce a rainbow. So when you see a rainbow, it's the water droplets that are refracting the light. And we talked about this already, but just to reiterate. When you see a blue sky, look outside, it's a nice blue sky today. The sky is not actually blue. It's not. The sun's light rays are getting refracted at an angle such that that angle produces only the blue part of the spectrum. Okay, that's what you're actually seeing. You're seeing the refraction. The sun's lights, though, are actually white. Now, it's not absorbing, but it's bending the light at a certain angle to produce only blue. A little bit different than the absorption part we talked about. Okay? Now, the other thing you might notice is when you see a sunset, you get the red, orange look in the sky. Sometimes you get a purple. Those are the ends of the spectrum because the angle. Listen, guys. The angle that you're seeing from the sun's lights changes because the sun is setting in the sky. The angle that it's coming to see your eyes with, that the light's rays are hitting your eyes with, are a different angle, which is why you're seeing the different colors. That's why you're not seeing the blue.
Well, when I was skiing, we saw a rainbow that was like around the sun.
Yeah, and it's funny that you brought that up. I was going to bring up a bunch of things in a minute to show you that. That's called a halo. It's called a halo.
Oh, the video game?
That's a video game, halo. And what I'm going to do, because we have some time, there's a bunch of cool links that I have on my bookmarks, and I'm going to show you. One of those is how a halo exists. It's very funny that you said that. And if you have a halo around the moon, you don't see the colors. But around the sun, you do. And we'll explain why. Okay? Max.
Wait, how does black absorb all the colors?
How does black absorb all the colors?
Like, how does that even get, like, how
Because it's the
nighttime
dominant.
Well, at nighttime, it's not that there's no absorption. There is no light. And nighttime is the absence of light. Black is the absence of light and the absorption of all the lights, of the light rays. So at night, it's not absorbing it all. Guys, stop. Come on. At night, you're not absorbing all the black. You're not absorbing all the colors to show the black color. What's happening is that there's absence of light there, which is why you're seeing it. That's the only difference, okay? So at night, it's not an absorption. Section is simply two problems on page 582, numbers 1 and 3. Okay, you're going to end up using the critical angle formula to determine theta C for those examples. Okay?